Hello and welcome to today's tutorial. This is the tutorial 3. This is based on class test 2, and here are some fill in the blanks questions. First question was, in adiabatic circuits the energy consumption can be reduced by increasing dash and or by decreasing dash. So, the answer is, in adiabatic circuits the energy consumption can be reduced by increasing T, that is the time for charging, and or by decreasing R. Let me explain to you how these two are coming. As you know, in adiabatic charging you are applying a variable voltage, say V T, and through a resistor, and here is a capacitor C, and maybe you will put one switch, and this is grounded. At time t is equal to 0, we assume that the capacitor on this charge is 0, and after that a voltage, I mean time varying voltage is applied, and this is the voltage V. And at time t, this is the time t, here you have the plot on this, in this you have got time. So, in time t it reaches a voltage, let us assume this is V c. So, whenever you charge with the help of this variable voltage, what is the energy that is being dissipated in R? That can be calculated, and this will be equal to energy dissipated in this capacitor R will be equal to R c by T into C V c square. So, that will be the equation that we will get. Now, this can be rewritten as 2 R c by T into half C V c square. Now, you note that this is the energy that is being dissipated in non-adiabatic charging. This is adiabatic charging. Now, with respect to this, we find that in adiabatic charging, whenever you are doing in this way, charging with the help of a variable voltage which varies over time, we find that this factor is multiplied by 2 R c by T. Now, when T is equal to 2 R c, then this becomes 1, and obviously the energy that is dissipated for charging the capacitor to the voltage V c c will be equal to half C V c square, which is same as non-adiabatic charging. However, when T is greater than 2 R c, that means you charge over a longer period, then what will happen, this factor will be smaller, that means this will be less than 1, and obviously the energy that is dissipated will be lesser than the non-adiabatic charging. So, you can one way of reducing the power dissipation, energy consumption can be reduced by increasing T. Another possibility is that you can reduce the value of R. So, keeping T, reducing the value of R, also you can reduce the energy dissipated in adiabatic charging. So, that is the reason why here is the answer. In adiabatic circuits, the energy consumption can be reduced by increasing T and or by decreasing R. As I mentioned, by increasing T, the power dissipation decreases because the voltage across this resistor reduces whenever you charge it slowly. That means, the energy dissipated across this resistor is reduced. So, if it is it can asymptotically increase, it can become 0 whenever T is very large. So, T is infinity, then obviously the power dissipation will be small. But however, in real life what you can do, you can make T as long as possible, and as a consequence the voltage difference voltage that is applied across the resistor R decreases. That means, the charge, whenever you keep on charging, the voltage here, that is being built up because of charge accumulation in C will be very close to VCT, and then as a consequence voltage difference will be delta V, and that will be smaller and smaller as you increase T. So, that is the reason why by increasing T you can reduce power dissipation. Now, the second question was older process technologies have dash constant and present day technologies have dash constant leading to larger dash loss. So, the answer is older process technologies have one sided constant and present day technologies have two sided constant leading to larger yield loss. You may recall that because of process parameter variation, the channel length varies in this manner. So, this is the typical L say typical, and around it changes, it is a random variable, and assuming Gaussian distribution you can see the channel length is varying over certain range, it cannot be considered as a constant. Now, as you know, in older technologies say less than 180 or you can say greater than 180 micron technology, what was happening in whenever 0.18 micron technology, 180 nanometer technology. So, whenever the technology was greater than 180 nanometer, then what was the situation? The leakage power was insignificant compared to dynamic power. So, when leakage power is insignificant compared to dynamic power as you know is proportional to CL VDD square F. Now, in this whenever you change the channel length, when the channel length varies over a range, this parameter CL changes, because whenever the channel length is longer, obviously the capacitance will be more, because CL is proportional to L into W. So, as the length increases, the capacitance increases, and as L decreases, capacitance decreases. So, the one sided constant was like this, that means the dynamic power dissipation was increasing like this. This was the dynamic power, and similarly delay was also increasing with the channel length. So, we can see here the because of this, the both channel length, I mean both the in this direction you will have delay and power. So, delay increases because of the increasing capacitance. So, this is your delay and this was power. Now, if your power budget is exceeded here and delay budget, that means performance is exceeded here, then this is the yield window. This is the yield window that you will get. That means, the devices which are falling in this range, that means for having channel length in this range have to be discarded. So, this is the one sided constant in older technologies. However, in the present day technologies, say in 70 nanometer or say maybe 45 nanometer, as you know, the static power dissipation is greater than dynamic power. That means, not only static power is significant, but it is more than the dynamic power. As you know, in 70 nanometer it is about 52% of the total power, that means static power dissipation is larger. So, in such a case what will happen, as the channel length decreases, what happens, because of VTH roll off, the threshold voltage decreases. That means, with the decreasing channel length, the threshold voltage decreases, and as the threshold voltage decreases, the leakage current increases exponentially. As you know, that subthreshold leakage current is dependent on the threshold voltage, and as a consequence the power is now like this. So, in new technologies, this is the, you can say this is old, this is also old technologies, and this is the new technology. So, in this case what is happening, because of power budget, you can say for delay budget, let us assume this is the window. I mean, you have to discard these because they are not satisfying the performance, but because of power, because of heavy leakage, let us assume this is the maximum leakage power dissipation or total power dissipation that you can tolerate. So, you find that in this here you have to discard additional devices and or additional devices dies because of the increased power dissipation. So, now you have got two sided power constant. So, in older technologies it is one sided constant. In new technologies we find that in the present day technologies it is a two sided constant, and because of this constant, two sided constant, what is happening, more dies are to be discarded, leading to yield loss. So, that is why here old process technologies have one sided constant and present day technologies have two sided constant, leading to larger yield loss. So, that was the second question. Coming to the third question, adaptive body biasing is a dash technique that allows tuning of each die to achieve dash. So, answer is adaptive biasing is a post silicon technique that allows tuning of each die to achieve higher yield. So, as we know, we have discussed several techniques of reducing power dissipation. I mean, to achieve higher yield. That means, adaptive body biasing is a technique that allows tuning of each adaptive body biasing is a post silicon technique. We have discussed, we in our lecture on variation tolerant design, we discussed some techniques which are post silicon and some techniques which are pre silicon. So, pre silicon techniques are essentially designing using suitable techniques, so that the variation is tolerated. So, you will do the design in such a way that it will be variation tolerant. On the other hand, in post silicon techniques, after the fabrication you will do some adjustment that can be done by applying different supply voltage or by applying different body bias. So, different dies will be applied different body bias. So, the answer is adaptive body biasing is a post silicon technique and that allows tuning of each die to achieve higher yield. Okay. So, that was the third question. Fourth question was, dash is a standby leakage reduction technique and dash is a runtime leakage reduction technique. So, I have discussed several standby leakage reduction techniques, and you may write any one of them here. So, either variable threshold voltage CMOS, VT CMOS, where you can change the threshold voltage by changing the body bias, or empty CMOS, where you can do power gating when in the standby condition, or you can do transistor stacking. That means, so far as the standby leakage reduction techniques are concerned, standby leakage reduction technique, there are several techniques. One is transistor stacking, or which is self biasing. As you know, if you apply different input combination to a combinational circuit, when the transistors are in series, because of self bias for a particular input voltage, there is reduction in leakage power, that is the transistor stacking. So, you can write transistor stacking or VT CMOS, variable threshold voltage CMOS, in which the threshold voltages varies by changing the body bias. And third technique that was discussed is empty CMOS, multi threshold voltage CMOS, where you can use multiple threshold voltage in series, you may recall. So, this is the actual circuit and you can put transistor either in the as header or footer to reduce the leakage current. So, this is also known as power gating. So, you can use any one of the three techniques, right, even in any one of the three techniques here, VT CMOS, MT CMOS or transistor stacking, and similarly for runtime leakage reduction technique, the most common approach is DT CMOS, where dual threshold voltage CMOS is used. That means transistors, some transistors are which are on the gates which are on the critical path, those gates are realized with lower threshold voltage, and gates which are on the non-critical path, they are realized by using higher threshold voltage. So, DT CMOS is one of the runtime leakage reduction techniques, and so this is the answer you can give. Then question 5 was voltage scaling reduces leakage power dissipation because of dash and dash. You may remember that voltage scaling is commonly used for dynamic power, for reducing the dynamic power, because you know that dynamic power is proportional to VDD square. But you can say there is a side effect. Side effect is that if you reduce VDD by several techniques, it can be static voltage scaling or it can be dynamic voltage scaling. Whatever you do, as you reduce the supply voltage, the leakage power reduces because of two factors. One is your drain induced barrier lowering. So, when the drain voltage is reduced, the barrier is lowered, barrier lowering occurs, and you as a consequence as the supply voltage is reduced. So, the barrier is higher, and as a consequence you know the leakage current is lesser, that means threshold voltage is larger. Similarly, GI dual effect, that is your gate induced drain leakage, that also affects the voltage scaling, and for larger voltage the leakage current due to GI dual effect is more, and for smaller voltage is less. So, because of these two effects, you know, as you do voltage scaling, there is leakage power reduction. Then coming to 6th question, signal isolation is used in power gating circuit to overcome dash. The answer is signal isolation is used in power gating circuits to overcome short circuit power. You may recall that. So, whenever you are using say multiple voltage domain in a circuit, let us assume this is a power gated block. So, this is a power gated block. So, since this is power gated block, the output voltage that is generated here, it can be either 0 or VDD, but for example, if you use say a header switch, then the voltage will be, as you turn it off, voltage should come down to 0, but it may not come down to 0 because of various reasons, because of the leakage power of this part, because of leakage power of this part. Even when it is switched off, there is some leakage current that will flow through it. As a result, there will be a voltage that will be generated here. So, if this output goes to a non power gated block, so this is non power gated. Then what happens? If this voltage is greater than VTN is greater than VTN and less than VTP, VDD minus VTP, then what happens? If it is greater than this, that means V in, that V out, you can say here V out is greater than VTN, but less than VDD minus VTP, then what will happen in this part of the circuit, there will be short circuit power. As you know, for example, in case of an inverter, if the voltage is input voltage is greater than VTN, this transistor is on, and if the voltage is less than VDD minus VTP, this transistor is also on. As a result, both the transistors will be on, leading to short circuit power or crowbar power. So, this is the situation, and that is the reason why this output is isolated with the help of suitable hardware. So, we will put an AND gate here, this output will be fed, sorry, you will put an AND gate here, this will go there and this will come here, and isolation signal will be applied here. So, that whenever this is isolated, this will be clamped to low level, so that it does not disturb this part of the circuit. That means, this is low, this will be low. So, this gate of course has to be it should get always, this should this AND gate should not be power gated. So, this is how it can be done. So, signal isolation is used in power gating circuit to overcome short circuit power. So, signal isolation can be done with the help of AND gate, OR gate, or some other hardware, as I have already discussed in detail. Coming to question 7, empty CMOS based power gating is used to minimize dash leakage power. So, as you know, empty CMOS based I have already discussed, empty CMOS based power gating is used to minimize standby leakage power. Empty CMOS based power gating is essentially you are putting the high FET transistors in series. So, you will be applying slip control signal here, and that will, and when the circuit is in standby, then these transistors are off, and as a consequence leakage power will be less. So, you can say this empty CMOS is used to reduce standby leakage power. So, empty CMOS based power gating is used to minimize standby leakage power. Okay. So, coming to question number 8, in dual FET circuits, the high FET transistors are used for dash and low FET transistors are used for dash. So, whenever I have already discussed about DT CMOS, as you know, in dual FET circuits, high FET transistors are used for leakage power. That means, in a multi-level, multi-input circuit, you have got many gates, and a larger portion of them are in non-critical path. So, the gates which are on the non-critical path, you can use high threshold voltage transistor to realize them. So, that will reduce the leakage power. So, high FET transistors are used to reduce leakage power. On the other hand, the gates on the critical path, they are to be realized by using low FET transistors, so that performance is maintained. So, you can say high FET transistors are used for leakage power, or rather to reduce leakage power, and low FET transistors are used for performance, higher performance. So, lower leakage power and higher performance, you can see. Okay. Coming to question number 9, multi-FET transistors can be fabricated using dash and dash techniques. So, I have discussed several techniques by which you can realize multi-FET circuits, that means transistors with multiple threshold voltages. So, the various techniques are, number 1 is multiple oxide thickness, it can be multiple channel length, you can use multiple body bias, so these are some of the techniques that I mentioned, and also you can do multiple channel doping. So, I have discussed how these techniques can be used and how the threshold voltage varies as you realize transistors with different silicon dioxide thickness, that means the width of the silicon dioxide layer, in realizing transistor. Similarly, multiple channel length, I have already mentioned that smaller the channel length, larger is the threshold voltage, smaller is the threshold voltage, that means because of VTH roll off. So, as the channel length reduces, threshold voltage decreases. So, multiple channel length can be used to realize multiple threshold voltage. Similarly, multiple body bias can be used to realize transistors of different threshold voltages. Similarly, multiple channel doping. So, you can write any one of the two, any two of the four. So, multiple TOX, that means multiple silicon dioxide thickness, or multiple channel length, I have channel doping I have written, but you can write any two of the four techniques that I mentioned. Then question number 10 is leakage reduction in transistor stacking occurs because of dash and dash mechanisms. You may recall that whenever you do transistor stacking like this, say several transistors are in series, say and depending on which of these are on and off, the leakage current varies. As for example, you have applied 0 voltage, 0 level voltage, and now some leakage current will flow, and as a result some voltages may be say 0.18 here and maybe 0.36 volt here, and some other voltage here, maybe 6.64 volt here. So, as you can see, some positive voltages are developed as these source points, and this leads to reduction in leakage current because of three mechanisms. Number one is, as you know, since the source voltage is positive and gate voltage is negative, gate is reverse biased, and as you know, whenever you reverse bias gate with respect to source, this reduces subthreshold leakage current. So, reduced subthreshold leakage current. Second is, the voltage across this transistor is small. As a result, because of that DIBL effect, because of smaller voltage across the transistors and with a smaller drain voltage, the DIBL component of leakage current will be smaller whenever you do this transistor stacking. And third reason for reduction is because of reverse body biasing. So, reverse body biasing is will lead to smaller threshold voltage, I mean larger threshold voltages, and as a consequence the leakage current will be smaller. So, you can write any one of the three. So, I have written reverse body bias and DIBL. So, any one of the three techniques, it also reduces subthreshold leakage current. So, you can write any two of any two from the three mechanisms that is responsible for leakage current reduction in transistor stacking. Okay, coming to 11, maximum switching activity for data transfer in 2's complement form occurs when dash is smaller and data dash. You may recall that there are two parameters, dynamic range and correlation factor. These two parameters are responsible for reduction in reduction in dynamic power. So, because of reduction in switching activity. So, when the dynamic range is small, as you know, because of in 2's complement form, what happens that sign extension occurs. Because of sign extension, as the if it suppose it changes from plus 0.3 volt to minus 0.3 volt and dynamic range is say 15 volt, then what will happen, the most significant bits In this case, for positive these are 0 and for negative it will be 1, and as a consequence there will be lot of switching activity. So, when the dynamic range is small and the sign changes in 2's complement form, that leads to larger switching activity. Similarly, the correlation factor, because of correlation factor the switching activity changes. For example, if the input changes slowly, increases or decreases, then the consecutive data are anti-correlated, correlated. As a consequence, the switching activity will be less. On the other hand, if it changes, say from negative it goes become positive, then it becomes negative and again it becomes positive. So, it is highly anti-correlated. So, in this case again lot of changes will occur, or if you can say if it changes very quickly, then data is anti-correlated. So, in these two situations, that means when the dynamic range is small and data is anti-correlated, the switching activity, maximum switching activity occurs using 2's complement form. And as I mentioned, this can be reduced by using sign magnitude representation of data when you send it over some bus. Okay. Question number 12 was module level clock gating is identified by dash, whereas resistor level clock gating is commonly identified by dash. You may recall that this whenever you are using power gating, you can either use some automated CAD tool, but whenever the module level clock gating is done, I mean here it is clock gating not power gating, the clock gating is done in module level, say ALU, then say transmitter, receiver, when they will be off, these are usually identified by the user. That means, module level clock gating is identified by the user or the designer. On the other hand, when the clock gating is automated clock gating tools are used, massively clock gating techniques are available nowadays, where CAD tool does the clock gating automatic insertion of clock gating hardware in the circuit. So, in such a case the CAD tool does the necessary clock gating. That is the reason why the answer is module level clock gating is identified by the designer, whereas resistor level clock gating is commonly identified by CAD tool. So, coming to question number 13, bus inverse coding is dash and dash encoding technique. You may recall that there are several ways by which the coding techniques can be categorized. One is your one category is redundant, another is non-redundant. Then whenever you are using redundant encoding, there are two alternatives. One is your one to many static, or it can be one to many dynamic. So, these are encoding techniques. Redundant means the whenever you are sending, here is your encoder and here is your decoder. So, to the encoder say n bits are applied and it generates m bits. When m is greater than n, then it is redundant, and as you know, when m is equal to n, then it is non redundant. So, when more number of additional bits are used, it is redundant technique, and there you can have two possibilities. In the first case, you know, you have got encoder and decoder. Encoder with memory, encoder with memory, and decoder memoryless. This is a situation one to many static. That means, in the encoder you will be using memory and decoder will not require any memory, and that is the situation in Bass inversion encoding. So, it is a redundant and one to many static encoding technique. On the other hand, you may require both, I mean encoder and decoder may have memory, that means, both will be with memory. So, sorry, this is the encoder with memory and decoder also with memory. In such a case, we call it one to many dynamic. That means, when encoder with memory and decoder with memory, it is one to many, and as you know, I discussed T0 encoding. In T0 encoding, you may recall that memory is required in implementing the encoder as well as the decoder. So, it is a one to many dynamic technique. But so far as this particular technique is concerned, Bass inverse encoding is concerned, it is a redundant and one to many static encoding technique. So, coming to question number 4, it is necessary to introduce dash when a signal is sent from a low voltage domain to high voltage domain circuit. So, it is necessary to introduce level converter when a signal is sent from low voltage domain to high voltage domain circuit. So, reason is same as you know, whenever signal is passing from I discussed about techniques where you know you have got say 2 voltage domains. So, this is your low voltage domain, say maybe say 1.2, and it is going to another voltage domain, and here let us assume the voltage is 2.0. So, whenever a signal low voltage domain signal goes from low voltage domain to high voltage domain, what happens, this voltage will be, there is a possibility that output level voltage will be in this range. It will be less than, that means, V out will be greater than V t n and less than V d d minus T p, and that will lead to you know short circuit power dissipation in this part of the circuit. So, to avoid that, we will be introducing level converter L C, and that will be fed back instead of directly applying. So, you will be using level converter, which will raise the level to high level, raise the low level to high level as the signal goes from low voltage domain to high voltage domain. So, the answer is you have to introduce level converter when a signal is sent from a low voltage domain to high voltage domain circuit. Question number 15 is, if feature size of a MOSFET device is reduced by a factor S, the device delay and power of the scale device become dash and dash respectively. Answer is, if feature size of a MOSFET device is reduced by a factor S, the device delay and power of the scaled device becomes 1 by S. You know this occurs because you know you are reducing both 3 parameters you are reducing. One is length, second is width, and third is silicon dioxide thickness. And as you increase the width and that capacitance C g is proportional to is dependent on 3 parameters W, L and C g, sorry that T O x, and actually T O x will influence in different way than W and L. So, as you increase W and L, I mean reduce W L, it will be W by S and it will be L by S. On the other hand, as you reduce the silicon dioxide thickness, what happens, the capacitance increases. So, here the parameter will be multiplied by S. So, effectively gate capacitance will be C g dash will be equal to C g by S, and as a consequence the delay will reduce by a factor S, and the so far as power dissipation is concerned, it will be proportional to 1 by S square, because you know because of the reduction in voltage, and that will also reduce, and it will also reduce the drain current. Because of reduction in voltage as well as reduction in drain current, the power dissipation power dissipation is equal to P by S square, reduces by a factor of S square. So, I have discussed it in detail. Coming to question number 16, code morphing software used in Crusoe processor is dash. Essentially, it is a dynamic code translation software. As you know, that code morphing software translates from one instruction, one type of instruction of a processor to another type of instruction set. So, from say that you are using, for example, your Pentium processors, which are essentially realized by using superscalar technique. On the other hand, that VLIW technique is used in realizing Crusoe processor. So, one instruction set instruction architecture to another instruction architecture, it does the translation, and that is why it is called dynamic code translation software. Essentially, it translates code from one type of processor to another type of processor. So, it is a dynamic code translation software. Coming to question number 17, realize a fully adiabatic 2 input AND OR gate. I discussed about the steps that you have to follow in realizing in converting a non-adiabatic gate to a adiabatic gate. First thing to be done, replace each of the PMOS and NMOS devices in the pull up and pull down networks with T gates. Second is use expanded pull up network to drive the true output and use expanded pull down network to drive the complementary output. Third is both networks of the transform circuit are used to charge and discharge the load capacitance, and fourth is replace DC VDD by a pulsed power supply with varying voltage to allow adiabatic operation. So, let us consider 2 input OR NOR gate. So, non-adiabatic invert 2 input NOR gate is realized in this way. So, you will require to so this is NAND. So, this is not NAND. So, it will be this is the NOR gate, 2 input NOR gate, that is realized by using non-adiabatic technique. So, you have to convert it, say here you apply A and B, and you can write A and B. So, this is the NOR gate that you can realize by non-adiabatic technique. You have to convert it into adiabatic circuit. So, you have to replace each of these transistors by a transmission gate. So, what you will do, say let us consider this part. So, here you have got 2 PMOS transistors in series. So, you will put 2 transmission gates in series, and this will drive a capacitance. And what will be the inputs? So, here you have applied A and B. So, you will be A and B, and here will be B bar and A bar, and here you will get NOR output, not that means A or B bar. Now, then you will realize this part. So, we have considered this part, and now we shall consider the pull down network. So, pull down network 2 are in parallel. So, you will require 2 transmission gates in parallel, and that will drive the output capacitance. So, here you will get OR, and what will be the inputs? So, A and B will be here applied here, A and B, here will be A bar and B bar. So, and finally, here the last step is you will be applying pulsed power supply, that means you have to apply pulsed power supply. So, you are realizing OR, that means A plus B, and this is realizing NOR, A plus B bar. So, this is how you can convert any gate CMOS gate to a fully adiabatic gate. This is fully adiabatic gate, because it does fully adiabatic charging and discharging with the help of this pulsed power supply. So, we will have dual output NOR and OR, and how it can be realized I have explained. So, this is the realization. Coming to question number 18, find out the switching activity of a modulo 7 counter using binary and gray codes for static encoding. So, this is the binary code, and this is the gray code. So, you can see here in a counter, the transition occurs, I mean it will go from say S0 to S1, then and in this way it will go to S7, and again it will come back to S0. So, this is how the counter occurs, I mean operates. So, you can the various states are, if we use binary coding, S0 is 000, S1 is 001, then 010 and so on. So, you have got, it has got 7 states because of 7 codes, and whenever it goes from 000 to 001, so transition is 1. Whenever it goes from 001 to 010, transition is 2 because 2 bits are changing, and from 010 to 011, 1 bit changing, and from 011 to 100, 3 bit changing, and from 100 to 101, 1 bit changing, and from 101 to 110, 2 bit changing, and whenever it goes from 110 to 000, 2 bit changing. So, number of transitions is 12. On the other hand, if you do gray coding, the codes are 001, 000, 001, 011, then 010, then 110, 111 and 101. And you can see for these 6 from these 6 transitions, the only 1 bit will change, 000 to 001 1 bit, 001 to 011 another bit change, and from 011 to 011 1 bit change. So, there will be 6 1 bit changes will occur. However, whenever it goes from state 7 to state 1, so 101 to 000, there will be 2 bit changes. So, total number of transitions is 8. So, you can see how the switching activity changes in modulo 7 counter for the 2 cases, binary code and gray code. Okay. Then the question was 19, question number 19 was, prove that the charging of a capacitor C in n steps to a voltage VDD instead of a conventional single step charging reduces the power dissipation by a factor of n. So, whenever the charging is done in one step, as you know, the power energy that is dissipated is CL V square by 2, where V is the voltage. And as you do n step charging, and obviously in each step the voltage charges from in the first step from 0 to V by n, in the second step V by n to stepwise it will keep on doing. So, you can see here energy dissipation in each step of charging will be CL V square by 2 n square, because the voltage here is V by n. So, CL by 2 into V by n square. So, that gives you CL V square by 2 n square. So, this is for each step of charging. Now, you will require n steps at charging. So, the n into each step, that will be equal to CL V square by 2 n, and if you compare with the first case one, that means the first situation one step charging, each step by E is equal to 1 by n. Okay. Okay, now let me consider some other questions. So, there are several questions you have given. So, So, one of the questions were adiabatic logic circuits operations. I have already discussed that adiabatic logic circuit, and another question was the normalized delay sizing, how the delay changes with sizing factor. So, let me answer the questions which can be discussed in this short time. One question was, as you this is the sizing factor and this is the normalized delay. What do you really mean by sizing? Sizing means you are increasingly increasing the size of the transistors. How you are increasing the size? Obviously, by increasing W. By increasing W, we are increasing the size of the transistors, and how the delay changes as you increase the fan out. That means, that there is a relationship between fan out and sizing factor. So, when the fan out is small, so when the fan out is small, the delay with sizing factor changes this way. That means, initially as you increase the size, the delay reduces, but after some time delay does not as you increase the fan out, delay increases. The reason for that is as you increase the size, there are two things. You are driving an say inverter of a larger size. Now, if this capacitance is large, the capacitance delay will reduce if you increase the size of this transistor. But that as you increase the size of this transistor, the capacitance of this also increases, and as the capacitance of this increases, there will be larger delay for this side. That means, that is the reason why for a given capacitance there is an optimal value of size, and beyond that it will increase, because driving the capacitance is increasing of this, that will lead to larger delay here. So, there is a optimal size for which it will get minimum delay, and beyond that, as you if you increase in sizing factor, then delay will increase. Now, that will be dependent on the fan out. Fan out means different value of capacitance. If the capacitance is small, then the effect of sizing is small. That means, reduction in delay is smaller when the capacitance is small, and reduction in delay will be larger whenever this capacitance is larger. So, when this, that means, here fan out is 6 and here say fan out is equal to 3. That means, when the fan out is smaller, that means, this capacitance is smaller. Fan out means it is driving a lesser number of gates when the fan out is equal to 3, and whenever you are driving more number of gates, then fan out is more. So, capacitance is more when the fan out is more, and that sizing will have more impact on delay when the fan out is more, and when the fan out is less, it has lesser impact. However, again there is an optimal sizing factor beyond which delay will increase in both the cases. So, that is what I explained. So, I believe the other questions we can take up in the normal class, and we can discuss in detail. So, with this let us conclude this tutorial 3, and you can take up other questions in our normal class. Thank you.